Yeah, thanks so much, Toby. Hi, everyone. I'm Long. It's my pleasure to present our recent work today here. The title is Data-Driven Aerodynamic Shape Design with Distributionally Robust Optimization. In short, DRO, this is a joint work with Jan, Lisa, my postdoc advisor, Professor Niklas Skauger, and Professor So in this presentation, I will first give a motivation and introduction to the data-driven design framework with DRO. So what we mean by this, and then I will talk about the connections and differences between DRO and the classical robust design optimization, which is well known in engineering community, engineering design community. And then I will present results and, of course, implementation, and finally give the conclusion. So we are interested in optimization under uncertainty. In the modeling of aerodynamic shape optimization, there may exist uncontrollable and unknown variations in problem data. For example, this can be the Mach number and lift. So to deal with this uncertainty, the multi-point optimization was developed and is considered a standard approach in practice. Sorry. But the main shortcoming of this approach is the selection of appropriate flight points and their associated weight. So here the x is the shape variable, omega here is the weights. On the other hand, the increasing amount of available data allows an unprecedented insight into these uncertainties. For example, in this figure, we plot the data of a real flight flying from Helsinki to Munich. And if we follow the multi-point optimization formulation, we can write the objective as the sum of all the data points. And if we additionally assign equal weight to each of the data points, we get the empirical distribution. And then the objective becomes the empirical mean of the objective. And this is a standard way or statistically principled way to incorporate the data to engineering design. However, the empirical distribution is only an approximation to the true distribution. For example, there may exist measurement error, the conditions, for example, the weather, climate, or the routes changes during the life cycle of product. And more implicitly, the design process happens before the mass production, and the data we collected only once after the product is built. So actually the data we collected, for example, from some heuristic lines, cannot be the true data for what we want to use for the optimization of the design. So instead of minimizing the expected value under the single empirical distribution, we want a design framework that is robust to the distributional changes. So you see here we have a maximization problem over a set of distributions. So this set somehow represents the possible changes in distribution. So this framework is called distributionally robust optimization. And let's formalize this idea. So DRO proposed to minimize the worst case expected performance over a set D. So the D we had before over set D of candidate distributions Q. Assume that this set D contains the true distribution. So important, of course, is here how we can define it. First, the D is called the ambiguity set. The common way to define it is in this equation 5. So the P here, is the nominal distribution or reference distribution. Rho here is the radius. And small letter b is the distance measure between two distributions. So the ambiguity set contains all the distributions whose distance to the nominal distribution that is the distance is smaller than the radius rho. In a data-driven context, we choose the nominal distribution to the empirical distribution that we have observed from the data. Another well-established formulation uses the soft penalty term delta instead of imposing the hard constraint and resulting in this penalized formulation. And we see in both the formulations, the distance measure D is the key that links the statistics to optimization. In this work, we use the phi divergence for the distance measure. Phi divergence of two distributions is defined here. It is a fundamental class of distance measured in statistics. So the phi here refers to a single variable function phi. Different phi of positive different distance. For example, we have chi-square divergence, KL divergence, and so many others. Assume we have now a nominal distribution that is uniform and has three supports. The ambiguity set that we have defined before with different phi and different rho is shown here. So we see here the chi-square divergence is basically a Euclidean ball, and other different phi divergence result in different shape of the ambiguity set in the probability vector space. The reason why we are interested in phi divergence is because it's strong connection to robust design optimization, and that I will briefly show in the following. So first, a brief review to the robust design optimization. The foundation for robust design was laid down by Taguchi, and one of his main contributions was his observation or his vision that one should design a product in a way to make its performance insensitive to variations in variables that are beyond designer's control. So in our case, the Mach number, the weather, and so on are the uncontrollable variables. And to achieve that, he proposed to optimize the mean performance while simultaneously minimize the variance. So the mathematical optimization formulation following this idea is the mean and variance optimization. So, and this is also really one of the most used formulations in robust design optimization nowadays. You should note that this mean variance optimization is commonly considered as a bi-objective function, bi-objective optimization. And here you see the factor mu, that is the weight factor that combines these two objectives. Recently, in the work of Goto and others, they have shown that actually the phi divergence DRO is asymptotically equivalent to mean variance optimization. Here we see on the left we have the DRO objective, on the right we have the variance objective, plus a term that is in the order of 1 over delta. Then the penalty parameter, we see that delta appears also in this weighting factor for these two objectives. And by duality, the larger the data, the smaller the robustness is considered. So if we consider this equivalence, then this the equivalence between DRO and the variance holds when more amount of robustness is considered because this term. So we note too that this equivalence that these authors have established applies to a wide range of different phi divergence. Because mean variance view or this mean variance formulation is fundamental to robust design, and in practice, sometimes we also consider a large amount of robustness. So we are interested what happens beyond the regime of small robustness. And we could show that with a particular choice of phi divergence, the chi-square divergence, then the equivalence between these two objectives holds for a much larger range of robustness. And we could also show the conditions for this equivalence to hold. To get a bit more insight into these connections, let's briefly look into the sketch of the proof. Again, we have at the beginning the DRO objective, that is a maximization over distributions using the fundamental duality theory and conjugate function in optimization. We can write the maximization problem to a minimization problem. Now it is only over a single Lagrange multiplier. So these two are equivalent. And this minimization problem entails its minimum if the lambda, the Lagrange multiplier, takes the value of or is equal to the empirical mean. So if we plug in the solution, then the minimization problem becomes the mean and variance objective. So it implies that the DRO objective using chi-square divergence is essentially a dual formulation of the mean variance objective, or we could say that the chi-square divergence is the dual view to the Taguchi method. To complete the comparison, we also found differences between these two approaches, which happens if we choose an even larger range of robustness, larger in the sense that this condition violates. So to give intuition, we just consider an example here. We consider a function that is quadratic in x and linear in xi. Assume x takes value from 0 to 1, and xi has 5 supports, and we plot 5 curves according to each support. Then the solution for the x that minimize the mean with respect to the xi is 0 because all curves are minimized at 0. And the solution for x that minimizes the variance is 1 because all curves go through 1. So if we apply mean variance optimization, which is a bi-objective optimization, then the solution Pareto front goes from 0 to 1, depending how you choose the weighting factor. For example, if you choose a large weight mu, then you get the solution close to 1. On the other hand, the solution of DRO is upper bounded by the solution of the robust optimization over the support, and the solution for that is x equal to 0 because again all the curves are minimized at 0. So no matter how large the robustness you choose for the DRO, the solution is no worse than x equal to 0. So this implies that DRO framework gives some guarantee to not generate too conservative designs. Now the last part, implementation and results. So we have a preliminary implementation in SU2, so that that's the shape optimization framework for deterministic design. The current implementation aims to be clear and simple. In the future, we would like to have a framework that is general for data-driven design problems, and that it can also take advantage of the modern algorithm in statistics and optimization. The optimization solver we use in this work is a new method called GDAM, was previously proposed by some of the authors. It is basically a gradient descent-like method that solves for inequality constraint problems. This work we have implemented a stochastic version of it and parallelized the sample evaluation. Now some results. First, we consider the shape optimization of RE 28, 22 in turbulent flow. We first consider deterministic shape optimization, minimize the drag subject to moment and thickness constraint. We compare the results of GDAM with SLSP. So we see that the resulting shapes are similar, and also the reduced drag are really close. Now let's consider also the DRO formulation, considering uncertain Mach numbers. And on the left, we see the 3 designs obtained from deterministic design, empirical mean design, and distributionally robust design. And on the right, we plot the performance in drag over the Mach number. And we see, of course, that clearly that the empirical mean design is more robust than deterministic design, and DRO design is the most robust one. And also the loss or the drop in mean performance of DRO design is relatively small compared to the empirical mean design. Right, now the conclusion in this work, we formulate and solve data-driven aerodynamic shape design problems using this kind of new DRO approaches. But we would like to point out there is actually a strong connection between the new formulation DRO and the robust design method that we use already a long time of Taguchi. The Taguchi method is formulated based on the statistic moments of cost, the mean and the variance. On the other hand, or on the other side, DRO is formulated based on the observed data with uncertainties. And we have uploaded a preprint. With that, I would like to thank you very much.
Other questions for everyone?
Yeah, I don't know if I missed that the design points of the
Mhm.
What did you do?
So in our, yeah, so the question was the design point, what I'm used for variant. So what are actually the uncertain parameter? In this test case, we used Mach number. Yeah.
No, I mean geometrically. So.
Okay, so.
Of the apple shape.
Yeah, so we use the Higgs-Hennes discretization with 38 variables. Yeah, it's a standard in, yeah.
Okay, are there further questions? If not, then
Okay.
let's thank Ronnie.